explain to you today. Therefore, many technical points I will jump, but we can discuss separately in some talk or privately as you want. So, but there is one point that you must clearly understand: a small change of notation. We start again with a vector space V, but now we consider its algebraic dual, and we denote the duality with the same symbol of scalar product. So there will, sometimes we could put even V here, but it's not a Hilbert space. It's a duality between the space and its own dual. And then we introduce, given the dual, then to every function V in V, we will associate the function xv, which is now defined not as we did in one dimension, on V itself, but on the dual. There is a reason for this. If you have some experience of, there is a reason for this. And if you have some experience of measure theory, you understand why we are doing this change of notation. So, to an element U star in the dual, we will associate the coordinate V in U star, which by definition is U star. So this is the canonical, standard canonical embedding of any vector space into its algebraic dual. Now, the reason why we take the dual is that when you study measure theory, typically a random process indexed by a certain space V corresponds to a probability measure whose support is not in V, but in V star. Usually V will have zero measure. So that is why we take this so that our notation will be the same in the infinite dimensional case. And as I insisted, the infinite dimensional case is an important development for this theory. We are working on it, but there is nothing published yet. So, but the notations that we develop are uniform and they are applied to the infinite dimensional case. So now we can these are functions. So since they are pointwise defined, they also any power of them is well defined. So I can speak of monomials of degree n in these functions. So I can speak of the polynomial algebra. I can speak of the polynomials of degree less or equal than n. Because you see, for every monomial, even if this map is clearly linear, you see, if I take a linear combination of that will be a linear combination. So the map is real linear, and the map that to V associates xv. And if I expand this, I still will obtain a homogeneous monomial of degree, an homogeneous polynomial of degree n. So this definition is intrinsic, it doesn't use basis. So I have this. Now, what is the technical point I will jump is the fact that I want to put now.
So you have xv from V star to the field?
No, xv from V star to the real numbers. Yes. Because this is a real vector space. But the complex comes because we take complex polynomials. So linear combination of monomial with the complex coefficients. So this will be our the typical polynomial will be the sum of zj of x v j to the power n. In fact, a little bit more. Well, you can prove by polarization that is the same.
Yeah, but my question define xv to the power n.
Huh?
What is this operator xv to the power n? It's a function.
Because it's a function. A pointwise.
Okay, you just
a
take the power.
pointwise operator. Just a pointwise. It is a function which is evaluated in one point, and you can define the function of any function by composition. Huh?
So it won't be a linear map anymore.
Of course. Only the first power is linear, but this is always only first degree polynomial are fine. Okay. So now this will be the element of the algebra. They will now what I will not discuss, but it requires a certain care, is first of all we have to introduce the statistics and the scalar product. Here we shall do a small digression because it is conceptually very important. So how, and it has to do with the notion of stochastic process. The traditional definition that you find, a very famous one, is the universally accepted, is in Doob, that the stochastic process is a family of random variables. But just this kind of this kind of developments lead to a small adjustment, because you see the big problem with Doob, it was already discovered. Well, let me not deviate of this, otherwise we will never finish. But let me just arrive to the point. So I tell you, I have to tell how to what is the analog of the probability measure on R that we introduced. Okay. Now, and I want to do this in an intrinsic way. So using this as a process, what happens? What is a random process? A random, in fact, we could say, to be more general, a random field on V defined on a probability space omega Fp. Okay, this is by definition a linear map which to V associates some process. Let me call it Y, not to confuse with this. We will identify them, but a posteriori. So it associates Y of V, which is a random variable, real valued, defined on this probability space. Okay, now once remember that, so this is an end. Remember, according to the standard Kolmogorov approach, the random fields are classified by their finite dimensional joint distributions, which means that if I take the probability of f of f1,
you want linearity or want linearity of the map?
Yes, it's a linear. Sorry, I didn't write. It's a linear map. It's a linear map from V to the random variable in that intuitively we should interpret YV as the component of a random field, of the random field Y along the direction. Okay, so to give a random field is the same thing as giving its components along V. This is what you do in elementary probability. When you take a vector valued function, how do you give it? You give it in coordinates. But if you give in coordinate, it means that you are giving a component on any vector, because you are fixing a basis. This is an intrinsic way to say the same thing. That a vector valued random. So, what is a random field? That is what I want to emphasize. A random field is a vector valued random variable. So, if U is finite dimension, and this dimension D, the random field is just a D vector, a vector valued random variable of dimension D. Okay? This formula has the advantage to be applicable equally to finite and infinite dimension. Now, what are the finite dimensional joint probability? I speak of expectation, not of probability. Remember that I use the same symbol for the probability measure for the associated integral. So with this convention, this is I will take a finite number n, and I take arbitrary Borel functions f, and I take this. So these are the fundamental objects, in the sense that if I have another random field y prime, such that these two objects are the same, they are considered from probability point of view the same process. Okay? This is very important. Why? Because it allows to say that these maps, the coordinate maps that we defined algebraically, are universal for random fields on V. Why? Because since I have this map, I will put by definition, so remember, these are real valued random variable. So the functions f a value are real values. So I will define now a probability measure P star on the dual. You see why I will define probability measure on the dual by saying that by definition the joint distribution of P star coincides with the joint distribution of this. So I will say that by definition P star of F1 x V1 times F n y V n, sorry, not y, x V n coincide. So since they, by construction, this gives me, now of course it gives me a probability on V star, because the coherence compatibility, the Kolmogorov compatibility condition are obviously satisfied, because we know a priori from this that this is a probability measure, so a fortiori this will satisfy the compatibility condition. So there exists a measure P star on V star which has this property. It means that I can always, if I have an arbitrary random field y on V, on the vector space V, that is always stochastically equivalent to the field x on the same space, on the same space, and the field x is defined by this map. Okay, so I have a universal model for random processing. So remember, what is a random field? A random field is a vector valued random variable. If the space V is infinite dimensional, the vector valued, the random variable will have values in an infinite dimensional space. Now that we have this, and we have established the universal environment, we have a probability measure. So to give a probability measure here, but we know that up to the uniqueness problem that I mentioned, there is a one-to-one correspondence between probability measures and states on the polynomial algebra. So we have probability measure P star. So is it clear the logic? we began as in one dimension purely algebraically. Then we introduced statistics because we introduce a random field on V. And we show that to give a random field on V is the same thing as to give a state on the polynomial algebra. So we associate the state phi on the polynomial algebra as P. Remember that P, of course, is P of V. Depends, this P depends on V, but it's fixed at V. And so we omit from the notation. Okay? Now we have the polynomial algebra. And we have the state on the polynomial algebra. Exactly as in the one-dimensional case, to the state we associate the scalar product. Sorry, this defines the scalar product on P. And we know that the coordinates are self-adjoint. The lemma extends without any difficulty to arbitrary dimension. I will not repeat. So remember the lemma that characterizes those scalar products that come from a state. They are characterized by this property. This property will be used all the time in the theory of orthogonal polynomials. Okay, so
can you just explain that statement once more? Y on V is stochastically equivalent to
What?
X on. Can you please explain once more that statement? Y on V is stochastically equivalent to X. What does it mean?
The statement is to give an arbitrary random field on V in the sense of this definition. So every random field on V in the sense of this definition is equivalent to the concrete random field X defined on V by the coordinates, where I define the probability measure or expectation or the state on V if you want. In fact, we will restrict to this. Here I am taking the Kolmogorov condition requires F to be arbitrary Borel function. Of course, we study moment equivalence, so the F we will restrict to polynomial. We know that if we restrict F to polynomial, we have a strictly weaker condition. So the general is for Borel F. But in any case, here we can use Borel F to define this term. It's clear? You see, to give a probability measure by the Kolmogorov consistency condition, it's sufficient that I give the joint probabilities. But to give the joint probability is the same thing as giving the joint expectations. And these are joint expectations of F. If you take the F to be characteristic function of some Borel set, you find the joint probabilities. You see? And you are in the standard formulation of the Kolmogorov theorem. Okay? Is it clear now?
Yeah.
It is. I say the philosophy is any random field in the abstract sense has a concrete realization with this random variable. So, in particular, this will be true when the random field P is a field with all moments. Remember our notation. But now, the probability measure is not on V, it's on V star. Of course, in one dimension you identify. Huh? Is it now clear? Huh? So, now you have the scalar product. So, if you have the scalar product, you can do the projection. This is a delicate point that I will skip. For each n. So, with this scalar product, P becomes a pre-Hilbert space. And you have to be precise in defining what is an orthogonal projection, we will call Hermitian projection in pre-Hilbert space. Is a technical point, this is not the main point. The main point is that these projections can be built, and we have an increasing sequence of projections like we have in the increasing means that if m is less or equal to n, then the Pm Pn is equal Pm, and moreover we know that the limit of the Pm is the identity in P. The limit in a very strong sense, in the sense that this limit, when I take on any element of P, stops and remains constant after f finite n. So it's not it's a limit we call such a limit a limit in the strongly finite sense, because any polynomial belongs to at least one of this Pn. And so since I have the projection on it starting due to this kind of filtration property, the limit will stop and will be always the same. Huh?
So the limit is in the
strongly finite sense. Strongly finite means that the limit stops. After a certain n, the range is what I have is constant. Okay, it's always the same because that is why it's convenient to work in algebraic level before going to the analytical difficulties. Now we have now this. Once we have this, we can form the orthogonal partition, the partition of the identity, because we define the orthogonal the projection onto the space of orthogonal polynomials of degree n. Okay, and due to this property, these polynomials will be mutually orthogonal. And will be a partition of the identity in the sense that this is 1. The identity in P. I use the symbol 1, but it's clear that it's an operator identity. Now, once we have this, we